So far in this chapter, we've gone through machine code, and we found that that was very difficult to deal with because these patterns of bits that correspond to the digital logic implemented into your CPU are very unintuitive as a programmer. We've made it slightly easy to understand by introducing the concept of these assembly mnemonics for things like loading a register into A, storing into A, and reading from memory. So we had now a text file that we could write that was easier for a human being to understand, and we even had pseudo instructions that we could write in this text file, and an assembler program would produce the corresponding machine code for us. And that was about making it easier for a human being to produce the code and to see what's happening in the code. I hope you agree that assembly is still quite difficult to understand, and that poses a problem because when you're trying to work through a solution to a problem, when you're trying to figure out how to go about solving a given problem, having too many details gets in the way. A much better strategy is to work top down, to think in terms of some very high level but non-specific tasks, and then to drill down on those. For instance, I want to read in a number, and then you can drill into, well, how do I read in a number, etc. And you can break that down into little pieces. Another important thing is if you try to solve problems in your code, in your text editor, in your code editor, you'll get it wrong. And then you'll go back and try to fix it, and you'll get it wrong again. And what will happen is you will have lingering bits of code or disorganized code that doesn't just have to do with how to solve the problem, it also includes lingering artifacts of every mistake you made along the way. The next guy who goes to look at it will have no clue what's going on, even if that next person is you. So what you do when you're an engineer, you see engineers walking around with engineering notebooks. You don't see enough computer science students do this, but you guys really ought to have some kind of a notebook on your desk. Some people have grid paper. I prefer blank white paper. But when you're going through to solve a problem, you have to draw pictures. You have to think things through. So here you can see some pictures. This I happen to have. I forget what problem I'm trying to solve here. Something to do with linear algebra. But you really want to work through problems on a piece of paper first. The thought process, the mentality, the way that you approach things with a pen and paper is different than what you do when you're on the computer. People think that they're able to just implement things or type things on a computer, but they're wrong. When everybody is. When you sit down and you work things out on a piece of paper, the solutions that you come up with are better. And you can see here, let me kind of try to find an example here. Here's an example of pseudocode that I wrote on a piece of paper to figure out how to solve this problem that I was addressing. And I drilled down and I drilled down until I came up with the right solution. And when I had to actually go to the computer and implement something, I got it closer to right earlier. I produced clearer code. And this is really important. So pseudocode is something for people, the thing that you write down on a piece of paper. It's not the actual code that executes it. There's no grammar rules, but you are trying to get as consistent and unambiguous as possible in your pseudocode. So here we have an example of pseudocode provided by the authors of your book. This pseudocode is on page... It's on page, I think, 180 of your textbook. And in page 180, if you read through, they kind of go through this example in more detail. And I don't think it's worthwhile for me to try to go through it here. The basic idea is this is code which is trying to convert an input number into a different base. So 93, this would be base 10 or decimal. And you want to convert it to a different base, like this would be octal, base 8. And the algorithm that they're going to do, it's written right here. And it is maybe not complete. There's some stuff that should happen first, like reading in a number. checking whether the quotient is not 0, divide by a new base. There's some details missing. Make the remainder the next digit to the left. It's still at a fairly high level, but it's kind of specific enough that as a person you can read that pseudocode and get the big idea of what's going on, especially when you see this example. So we can see here that 93 divided by 8 has a remainder of 5. The result goes here, divided by 6, that should be an 8. So we can already tell from the pseudocode that there's an error here. Divided by 8 gives a 1, gives a 1 with a remainder of 3, so that 3 goes there. That 1 comes over here. Divided by 8 has a 0, remainder 1, so that 1 goes here. We can work through that. Your book tries to do it with this little table of boxes. It's a good idea to try to learn how to trace through the execution of a program like this one, and have some notation to keep track of what happens to these things. So this is a variable, and you can kind of tell it's a variable from the notation that they've used. Decimal number, new base, and quotient would be some variables used by this pseudocode in order to solve the problem. And yeah, here we go. So a variable is really just a name that corresponds to where you'd store values. And you can do things with them. This is called gets. So if you say like A gets B, that means you copy the value of A. So you copy the value of B into A. So A is a variable. It's think of it as a box that can hold something. That's A. B is a box that can hold something. Whatever's in this box, you move it up into that box. So that's assignment. Output, you have those kind of operations in pseudocode. That's pretty obvious. You can write and print things. Input, you can get or read. You kind of want to stick to a consistent terminology in your pseudocode, and it'll make it easier for you to mentally translate your pseudocode into real code when the time comes. Another kind of high-level operation you want to do in pseudocode is called selection, which means you ask a question, and depending on the answer, you do either one thing or the other. So here I'm asking the question, is the number less than 0? If the answer is yes, then I'm going to do this little bit of stuff. Right? And you can get more specific. You can do extra things. We use indentation in pseudocode to indicate blocks. So I drew a little circle around some stuff, and you can treat this entire block of instructions as sort of a single meta operation. So if the answer is yes, you do this block of code. If number is less than 0, if that's yes, you do this block of code. And then regardless of what the answer is, when you're done, you continue. So here we have an example of you ask a question, is age less than 12? If age is less than 12, if the answer is yes, then you do this block of code here, right? This block of code, if yes. If the answer is no, you consider this condition. So this condition only gets executed if the answer is no, because it says else. So the word else means you only do it if the answer is no. So if the answer to age less than 12 is no, you check if age is less than 65. So if it's no, you have another decision to make. Is it less than 65? And if the answer to that one is yes, then you're going to execute this block of code. You execute that block of code, and here we've got an else, so that means if the answer is no, you're going to execute this block of code. And then finally, at the end, whatever the answer was, yes or no, you continue executing down here. So I hope that figure is clear. You come in to this chunk of code, you make a decision. If it's yes, you go here, and then you skip over everything else and continue the code. If it's no, you come here and you make this second decision, And if it's yes, you do this piece of code, and then you continue. And if it's no, you have no more decisions to make, you just do this piece of code and continue on with executing. So this is selecting either block of code A, block of code B, or block of code C based off of some decisions. I hope that makes sense. And by the way, this kind of a flowchart diagram where you use diamonds for decisions and rectangles for blocks of code is also a very good way of organizing. It's equivalent to, in some ways, pseudocode. So repetition, again, repetition is you've got a block of code, but instead of deciding whether you're going to do it 0 or once, you might do it multiple times. So here you say, is the count less than 10? And if the answer is yes, you do some block of code, and then you come back up to that decision. That's if the answer is yes. And if the answer is no, then you carry on executing without jumping over it, or just going ahead and jumping over it. So this block of code here might get executed 1, 2, 3, however many times. Right? In order to break out, this guy had better update count. So you hear we can't set count equal to count plus 1. Otherwise, you have what's called an infinite loop, or your program halts, hangs. So there's a little question here: how many values will be read? And this gets to tracing the code. So you need to trace this code very carefully. Count starts off as 1, and when it's 1, the block executes. Count gets updated to 2, and when it's 2, the block executes because 2 is less than 10. It gets up to 3, 4, 5, 6, 7, 8, 9. When it's 9, 9 is less than 10, so the block executes. And then it gets set to 10. But when it's 10, 10 is not less than 10, so the block does not execute. So how many times, and you continue on. So how many times does this loop repeat? 1, 2, 3, 4, 5, 6, 7, 8, 9. That may not be what you expected. Generally, if we're doing that BRLT for branch while less than, or using an equal comparison, we're not going to get that last step in. So we generally get count goes up to, but not including your limit value. It's okay if we start with 0. So we might start the counter at 0, which would give us our 10th repetition, 0 to 9. That's just a little trick. It'll come back and it'll bite you later. So here's another pseudocode example, and it starts high level, and we drill down to get more specific. I say it starts high level because our problem is to print each pair in order and read in pairs of positive numbers. So this pseudocode here you read in 2 positive numbers, that's good, but it leaves us with some really big glaring problems. How do we know when we're done, and how do we print them in order? I mean, that's the problem just repeated in the pseudocode, which really doesn't solve anything. This is not specific enough for us. However, this is a pretty valid step to go through while developing an algorithm. The next thing that you need to do here is we need to drill down on that guy. So we need to get more specific, and this guy too, on how we tell we're done and how we print them in order. So how can we tell if they're done? We can let the user tell us how many, and we can get more specific. We can display or print some sort of a prompt, and then we can read the number of repetitions. So we can get really specific on that with pseudocode. How can we tell if they're in order? Well, we use selection. If the first is smaller, then we do this block of code. Else we do this block of code. We know how to do that, and we can drill down and get specific in our pseudocode. So here we are getting more specific on how we can check if not done. Right? And of course this is part of it too, because we're checking if the number of read is less than the number of pairs we want to read. In order for that to be correct, we also need to increment at the end. So we can get more specific in that, and then here we get a little bit more specific on print in order. So we just drilled down on those two words in our pseudocode, and as a result we have something which is much more specific, and I think it's much more straightforward how we would translate this into some assembly code, for instance. I'm not going to do the walkthrough. I think I'll leave that to you. It's in your book. Hopefully you can figure that out. As you go through, or you could just use it to try to implement it and use a debugger. Speaking of implementing it, when I say implementing, I'm talking about translating that pseudocode into something that can be executed on your machine. So what can that be? It could be assembly language. It could be machine. You could try to go straight to machine code if you're a masochist. The assembly is generally very detailed and more time-consuming than we want to do. Very often we'll want to go to a high-level language, but we're not going to get to that until Chapter 9. Right now, we're still living in the nitty-gritty, ugly assembly parts. Right? A high-level language, by the way, you go from high-level language through something called a compiler. So there's a thing called a compiler. It takes high-level language and it produces assembly. And that, of course, goes into an assembler. Pardon the messy handwriting, trying to use the same notation. And then you get machine code or object code. And that goes into a CPU. I know this is kind of very hand-wavy, but this is the general idea of how you might go. And actually out here, you've got in your brain, you've got out here pseudocode. So this is a good way to think about things. And out here also you have diagrams and drawings. So you should be doing all of that stuff when you're thinking about problem solving, because programming, coding is problem solving. I'm going to stop right there and I'll do another video talking about testing, because it dovetails right into what I just said about coding being problem solving.